Lesson 6-4 is polynomial functions. We're going to evaluate functions and then identify general shapes of the graphs of different polynomial functions. So just to review, the degree of a polynomial is the greatest exponent of its variable, and if there's more than one variable, then you would add up those powers. And then a new vocab term, the leading coefficient. Coefficients are the numbers in front of the variable, and the leading coefficient would be the number in front of the highest degree term. So if we look at this example, it's degree 5, because x to the 5th is the highest power, and the leading coefficient is 3, because that's the number in front of the highest degree term right here. Now, in order to find the highest degree and the leading coefficient, it's typically best to write the polynomials in descending order of powers. So the highest power comes first and the leading coefficient, and then you've got the powers decreasing by ones on the way down. All right, so let's try a couple more of these. State the degree and the leading coefficient of each polynomial. So in letter A, we've got the powers of x in descending order. So I can easily see that the degree is 4, because that's the highest power on x, and then the leading coefficient is 7, because that's the number in front of x to the 4th. In part B, however, the powers are not in descending order, so if you wanted to rewrite it, you could always rewrite it and say that we really have a negative x to the 5th first, plus a 2x to the 3rd as the second highest power, and then plus x squared would have to go last. So the highest power here is 5, so we've got a degree 5 polynomial, and the leading coefficient is -1, because we've got a negative sign in front of that x to the 5th, so it's a -1 as our leading coefficient. Okay, example 2, now we're going to find some functional values. So you're going to be given a function and they're going to ask you to find a value like p of -1. So you plug in -1 in for each x, that's your input. So we've got -1 to the 4th power minus 3 times -1 to the 3rd power plus 2 times -1 squared minus 5 times -1 and then plus 1. And if you wanted to type all of this in on your calculator, that's fine. You just have to make sure that you have parentheses around your negatives. Now, I know that if I take -1 to any even power, it becomes +1. And if I take -1 to an odd power, it'll stay as -1. So I'm just going to start by simplifying these powers. Okay, so powers are simplified. If it's an even power, I know it'll become a positive number. If it's an odd power, I know it'll stay negative. Now I want to multiply next. -3 times -1 is +3. 2 times 1 is 2. -5 times -1 is a +5. And then we have a +1. And now I can simply just add all the way across. So we've got 4, 5, 6, 11, 12. There you go. So p of -1 is 12. In example 3, now we're going to plug in some variables along with these numbers. So we're finding p of 3a, and this time the function is 3x squared minus 2x plus 5. So anywhere I see an x, I need to plug in my input 3a. Okay, so 3a takes the place of x. So we've got a 3 times 3a squared minus 2 times 3a plus 5. And notice I always use parentheses when I'm plugging in these values. Okay, from there, following the order of operations, I'm going to evaluate the power first. So we've got 3a squared, that means 9a squared, minus 2 times 3a plus 5. Next, I'm going to multiply. 3 times 9 is 27, so I have 27a squared. 2 times 3 is 6, so I have minus 6a, and then plus 5. Now, none of these are like terms, so that's kind of where I stop. That's my answer, 27a squared minus 6a plus 5. Okay, moving on to letter B. This time a plus 1, this binomial, has to go in for each x in the original polynomial. So we've got 3 times our input squared. That means a plus 1 to the 2nd power. Then we're going to take minus 2 times a plus 1 and then plus 5. So here I've got a binomial to the 2nd power. That means I need to FOIL. So I'm going to keep this 3 out in front, and I'm going to worry first about FOILing a plus 1 times a plus 1. Okay, then I'll distribute -2 times a plus 1, and then we'll worry about adding 5 on later. Okay, so using FOIL, or you can just think of it as the distributive property, we get, I'll leave that 3 there, we get a squared plus 1a plus 1a, that'll add up to 2a, right? If you take the outside and the inside and add them together, you'll get 2a in the middle. And then last times last, 1 times 1 is 1. So we've got 3 times this trinomial, minus 2 times a plus 1, and then plus 5. We need to simplify all this and see what we get. Okay, so multiplying by 3 to begin with here, I get 3a squared plus 6a plus 3. That's 3 times each term in the trinomial. Then we're taking minus 2 times a, minus 2 times 1, and then adding 5. Okay, now finally let's combine any like terms, and I always go in descending order. So the highest power here is a squared, so we're going to start with 3a squared. Then we've got some a's to put together. 6a minus 2a is positive 4a, and then we've got our constants. 3 minus 2 is 1 plus 5 is 6. So we get 3a squared plus 4a plus 6. That's our final answer. Okay, the last thing now is taking a look at graphs of various polynomial functions, and also what their degrees are. So there's something kind of cool about the way a graph looks and its degree. So beginning with the constant function, this would be something like f of x equals 5. It has degree 0 because there's no variable in it, and it ends up being a horizontal line at whatever that y value is. Degree 0, just a flat line. Now a linear function has degree 1. That means it stays increasing or it stays decreasing the entire time. It'd be something like x minus 5. A quadratic function has degree 2. These are the functions that are x squared plus 3x plus 5. So you've got a trinomial, that's a quadratic function. If it's degree 2, it starts off in one direction, maybe it's decreasing, and then it switches to a different direction, increasing. So you can kind of count the degrees. We've got 1, then 2, by the sign changes. A cubic function turns out looking like this. It's degree 3, and here's how I'd count it. It's increasing, that's 1. Then it switches here to decreasing, that's 2. And then it switches again to increasing, that's 3. So just by looking at a graph, you can actually tell its degree just by counting the different, changes in direction. So we've got 1, 2, 3. A quartic function is degree 4. That means the highest power on x would be 4, so it would have an x to the 4th in it. And the graph turns out looking like this. You've got 1, 2, 3, 4. Degree 4. And then finally a quintic function has an x to the 5th in it, and if I count again all of the different changes in increasing or decreasing, it would count like this: 1, 2, 3, 4, 5, and that's how I can tell that it's a degree 5 function. Now I want you to also notice something about even or odd degree functions. So if it's an even degree function, like 0, 2, or 4, it's always going to be symmetrical about the y-axis. It's a mirror image or a line of symmetry. Look at the quadratic function, same thing. It's symmetrical about the y-axis or some other vertical line. Degree 4 polynomial, it's symmetrical again. It's a mirror image on either side. So it's symmetric about the y-axis, or sometimes it's shifted left or right. It's going to be symmetric about some vertical line. If it's an odd function, an odd degree function, like 1, 3, or 5, it actually is symmetric about the origin or some kind of center point. So you can see that in linear functions. You can see that in the cubic function right here. It has rotational symmetry about the origin, or even in a degree 5. You can see that it's kind of a mirror image across the origin, or a rotational symmetry. Okay, so let's give it a try here in these few examples that I have left. So for each graph, we want to describe the end behavior, determine whether it represents an odd or an even degree polynomial function, and state the number of real zeros. Okay, so what does it mean by describing the end behavior? Well, you're going to write 2 sentences, and I'll show you how to structure them. Okay, you can also read about this on page 334 in your textbook. So if we're describing the end behavior, we want to know as the graph reaches its endpoints, even though we know it's going to infinity here, what's happening. So here's how you're going to structure your sentences. This is what you're going to want to remember, what you're going to want to write down. We will say that as x approaches, you use an arrow, as x approaches negative infinity, that means as the x values go to the left, where's the graph going? Well, this graph happens to be going down to negative infinity. So as x goes to negative infinity, our y values, or the function, goes to negative infinity. So you can put a comma in between and say that our function, f of x, which is graphed in blue, goes to negative infinity. And then you want to make a statement like this: as x goes to positive infinity, that means as the graph goes to the right, you know, because x goes from left to right, so as x goes to the right to positive infinity, where's our graph going? Well, this graph is going to negative infinity on the right side as well. So you would say that the function f of x is going to negative infinity. So this would tell somebody that the graph is going to negative infinity on each side. Okay, you can see that on the graph here. When you're going to the left or when you're going to the right, the graph is going down. So that's the first bullet point. Then part 2, we want to describe whether it represents an odd degree or even degree. This has to be an even degree, and I know that because it's the same on each side. It's symmetrical, so I know that it's even. It's symmetrical about the y-axis. I can even count it if I want to. If I count the changes here, we've got 1, 2, 3, 4. I know it's degree 4. So if you want to make a note of that, you can do that as well. And then finally, we need to state the number of real zeros. Well, the zeros on the graph are easy to find. The zeros are the places where the graph crosses the x-axis. Now, if it's a degree 4, it has a possibility of having 4 real zeros, but it might not always have 4. You can see that if this graph would have dipped below x and then back up again, it would have actually crossed 4 times. So a degree 4 polynomial has the possibility of having 4 real zeros, but it doesn't have to. So we can see that there's 2 real zeros. And what that means is the other 2 are imaginary. So the number of zeros will always add up to the degree. So we've got 2 real zeros. And just to make a note here, that means that 2 are imaginary or complex. I'm not sure how to spell it. I think it's an A. Okay. Imaginary. There we go. 2 are real and 2 are imaginary. Okay, let's try these. I know they're lettered a little wrong, so you can make this one for B and then the last one for C. Okay, so we've got the same 3 bullet points here, and the first one was describe the end behavior. Okay, so you want to start by saying as x goes to negative infinity, that means as we go to the left, where's the graph going? Well, our graph, or our function, is going to negative infinity. So f of x is going to negative infinity. Your second sentence should say as x goes to positive infinity. Of course, we're meaning as we move to the right. Where's the graph going? Well, this graph is going up to positive infinity. So as we go to the right, f of x is going to positive infinity. After that, we had to state if it was even or odd. And if you want to count the degree, you can. It's 1, 2, 3. It's degree 3, so it's odd. I guess the more information we put down, the better. And then finally, how many real zeros do we have? Now, because it's degree 3, we could have a max of 3, but I'm only seeing 1 real zero, 1 x-intercept, or 1 place where the graph crosses x. So you could say 1 real 0. And the zeros have to add up to 3, so that means that 2 are imaginary. We're kind of going above and beyond what the textbook is asking us to do here, but that's good. Okay, and then in letter C, let's take a look at the graph here. We first need to describe the end behavior. So we'll say as x goes to negative infinity, I always go to the negative side first, or the left side. As we move to the left, basically to the left of 0 here, where's our graph going? Well, it's going up to positive infinity. So you'll say f of x, the function, goes to positive infinity. And as x goes to positive infinity, that means, well, I forgot my x in here. As x goes to positive infinity, as we go to the right, where's our graph heading? Well, the graph for the function is heading down to negative infinity. So you'd say f of x is going to negative infinity. So they're backwards this time. Second bullet point, what's the degree? Well, the degree here is 1, 2, 3. It's degree 3. It's odd. And how many real zeros do we have? We have 1, 2, 3 places where our graph crosses the x-axis. So that means there's 3 real zeros this time. Remember, that's the most there could be. Okay, finally, I'd like you to try these just to check to see if you understood the first couple examples here. There is one graph left over in example 4 that you can also try on your own, letter B on that first slide there. So give those a try, bring them to class with you tomorrow, and we'll keep practicing.